Welcome back. So, now as I said before that we will be discussing consensus mechanism in Bitcoin blockchain. The main technical challenge, so digital cash has been thought about and many proposals have been made by computer scientists for almost 20 years before the 2008-9 when the Bitcoin blockchain was introduced, and that was the first cryptocurrency that we saw. So, always there was this question of the consensus that bothered people. Now, why is it important? Because when you create new money or when you create a new transaction, somebody has to validate that this is the valid transaction. Somebody also has to check that you are not double spending. So, you acquire some money, say let us say 25 bitcoins, and you pay somebody 25 bitcoins and again you pay the same 25 bitcoins to somebody else, that should be disallowed. Now, with a central authority that is very easy to check, but with a decentralized system it is much harder problem, because if one node here says that what you are doing is not acceptable, other nodes may say that what you are doing is acceptable. So, therefore, one has to decide that what should be the verdict of the entire network, right, because somebody might be maliciously saying that what you are doing is not acceptable when you actually did perfectly correct thing. In another possibility is that some of the good participants got fooled because you did something wrong, but you actually fooled them, or it could be that the number of malicious guys are trying to say some bad transaction as good transaction, like you have done double spending and then you have told your friends that you vote for me and you say that this is a good transaction, that transaction gets into the blockchain and it becomes permanent, that is not good. So, therefore, this consensus, so consensus is the mechanism by which you say all of us agree on something, to that something is acceptable. So, in a distributed setting, consensus has always been a problem, and this problem has been looked into almost for 40 years. So, let us see what are the things that happens. Now, consensus, as I said, other than in case of blockchain, how the consensus problem came about in the distributed computing community. So, in a distributed computing system, you have distributed set of nodes, and this set of nodes have to compute something, right. So, let us say they have to compute some function, or they might have to compute that some routing table, or they may have to compute, they may have to together maintain information and information integrity. These are the kind of things that distributed computing community worry about. Now, in order to have a distributed system work, many times people do what is called a leader election. So, you have n number of nodes, and then you run a protocol that everybody engages in, and eventually say here is the node that will be the leader. So, once I have done the leader election, I will listen to the leader throughout the computation. So, that leader can then give you work, that you do this amount of work, you do this amount of work, and together you accomplish something. So, that is basically called the leader election protocol. So, similarly, sometimes the distributed system has to do some voting. For example, for leader election also you may have a voting based leader election, but sometimes you have to vote on a piece of data, and therefore, you may have to do something called a consensus. So, this problem has bothered distributed computing people for more than 40 years now, and some of the applications they had thought about even before blockchain is that I may have to create a hash table, but I do not want it to be maintained by just a single authority. I want this hash table maintained by everybody. So, everybody will have a copy of the hash table, and this copy of the hash table should be the same. if you have that, then you can have a distributed domain name service. Earlier I said that the distributed domain name service right now is kind of centralized, but if you have a distributed DNS, then you know you are free from the dependence on a trusted party. Public key directory. So, when you have public key, remember like yesterday we discussed that if you have public key, telling everybody else that is your public key, and also convincing them that it is your public key requires digital certificates. Digital certificate is basically when a trusted third party tells the others that indeed it is your public key. Now, you can actually maintain a public key directory distributedly in a decentralized fashion through a distributed hash table, if you can solve that problem, and then other places like stock trades and so on. So, this has been a problem, distributed computing problem for a long time. So, how do we define the distributed consensus problem in a formal way? So, what we say is that distributed consensus is a protocol that terminates, and then all nodes that are not malicious decide on the same value, and this value must be proposed by at least one correct node. So, let us say you have n nodes. Nodes means these are computing nodes, and they are connected by some topology here, and they are going to decide on some value. So, everybody proposes a value. For example, if it is a binary consensus, then everybody proposes either a 1 or a 0. So, everybody proposes something, right, and then you run the protocol. At the end of the protocol, everybody should have, let us say among these two are bad actors, and they are proposing 0, everybody else is proposing 1. Now, during the protocol exercise, these guys will not also listen to follow the rules of the protocol. So, they will try to send messages, they might try to confuse the others, but if the distributed consensus protocol is robust enough, that is with the existence of this malicious guys doing malicious things, eventually all the good guys will decide on 1, because 1 was something that was proposed by one of them. Actually, in this case, in my example, all of them, but maybe this guy might have done something else, but what they agree on is 1. Then we know that we have reached a consensus. Now, since one of the good guys also did 0, in this case if everybody eventually agrees on 0, that would be also a correct outcome, because what it says is that the protocol terminates and all correct nodes decide on the same value, and that value must have been proposed by some correct node. Now, the only complication here is that protocol designer does not know how many are going to be malicious node here. Second thing he does not know is who are the malicious ones, right. So, therefore, the protocol has to be designed in such a way, so that no matter who are the malicious nodes, this consensus will eventually terminate and a consensus will be made, and the consented value by the good nodes, non malicious nodes, should be chosen from the values that were given by at least one of them. So, anything that the malicious guys proposed as the value, that should be chosen. If none of the other good guys have proposed that value, then that should never be the end result of the consensus. So, that is the idea. Now, it turns out that depending on what kind of maliciousness you are going to see in these nodes, the problems gets different. So, for example, in the very beginning people started saying that, well, if while the protocol is running, if one of the nodes crashes, so that is not really malicious, the node might crash for other reasons, even then the consensus problem becomes really hard, right. So, if the one of the node crashes, then also consensus problem becomes hard. So, this is called a crash fault. So, if we have a protocol that works in spite of crash of some nodes, then we say it is a crash tolerant or crash fault tolerant protocol. But in case it is protocol fails, that is it fails to terminate, or it terminates, but it gives a incorrect consensus, then we say that the protocol is not tolerant to crash fault. Now, crash fault is the most benign kind of fault, because the node that has faulted is not doing anything malicious, it is just crashed. Now, one problem in all this in the decentralized setting is that other nodes cannot tell whether the node crashed or he is maliciously keeping quiet to create confusion, right. So, therefore, we have to assume that the crash fault is could be a behavior of a malicious node, or it could be really crashed. Now, crash fault is the easiest of the maliciousness. The worst kind of maliciousness is called the Byzantine fault. So, Byzantine fault basically means that the nodes that are malicious, they are not only going to propose wrong values in the beginning, they are also going to not follow the rules of the protocol, and therefore, they will be doing things that are not part of the protocol. Protocols, what is a protocol? Protocol is a program for every node, right, and each program here could actually do some computation and communicate with the other nodes, and then again do some computation, communicate with other nodes. This is what a protocol looks like, right. So, a protocol then obviously has a set of rules, or how the program is supposed to run. The malicious nodes may actually run a different program. Maybe it is because they have been infected by a malware which has a different program, or it may actually do various things like exchange messages between the other malicious nodes and not ever communicate with the others. It can do all kinds of things. So, the question is, what we want in case of a Bitcoin case, for example, we also have to worry about nodes that will work maliciously. For example, they will validate transactions which are not supposed to be valid, or they might actually not validate good transactions, or they might actually create blocks, and that those blocks may be having invalid transaction in them, and broadcast that block for saying that this is the next block. So, they can do all kinds of things. So, that in that case also, which block has to be eventually added to the network next, to the blockchain next, is a consensus problem, right. And the protocol should be robust enough that even if some of the nodes act like that, we have the ability to eventually have a correct block added to the blockchain. So, how the peer to peer system works in blockchain in the Bitcoin is that whenever you want to pay to your friend Ravi some Bitcoin, you broadcast the transaction to every node of the network, saying that this is going to be Ravi's address, which is the hash of Ravi's public key, and you have to sign it, right, and you have to tell your public key also, and then you broadcast it to the entire network, right. Now, how the network broadcast it to reach all corners is a matter of the protocol that is underneath the Bitcoin protocol. It could be a gossip protocol, it could be other ways of broadcasting, it can be a multicast and things like that. So, now one thing I want to say is that while you are paying Ravi, it is not a synchronized throw and catch, right. Ravi may not be connected at that time. Later on, so all the other nodes will check if your signature is valid, and also it will check whether you have sufficient balance to pay Ravi, right, the amount that you are telling you are going to pay. All the other nodes will check that, and they will validate the transaction, and then eventually some nodes will create a block in which this transaction will be put in, and then eventually this block will be hopefully be part of the blockchain. Later on, Ravi, when he connects, he will see that there is a transaction which gave him money, and then after a while we will talk about that, like how long after Ravi can assume that he can even spend that money. So, that is the way this peer to peer system is working. Now, let us look at the growth dynamics. So, I have been talking about this for a while, but let us look at it more formally. At any given time, all the nodes that are maintaining a copy or replica of the blockchain will have a sequence of blocks on which the consensus has taken place, and there has been an agreement that these are the blocks that have been made permanent into the blockchain. So, every node will have some set of nodes that are already have gone through the consensus, and then each node will have a set of transactions that have not been part of any of these blocks, and they have to decide which of these transactions they will want to put in a block. So, they can decide that I will put only this, because the blocks have also a fixed size. So, they may not be able to put all the transactions that are still outstanding. So, these are the outstanding transactions, you have to select from them and then put in a new block, and every node that is part of the process is doing the same thing. They have a sequence of blocks and that are already consented on, and then they have a set of outstanding transactions. When you have these outstanding transactions, let us say in this example there are 3 different miners, and they are using, of course, the mining requires a hash puzzle solving. So, they have very high computing power and so on. So, this guy decides this set of transactions is going to be in the next block. This guy decides that these are the set of transactions in the next block, and this guy decides that these are the set of transactions in the next block, and there may be many reasons why these 3 are different. One possibility is that the transaction as they are broadcast, they take some time to reach or all parts of the network. So, by the time this guy collected some transactions, some of the transactions have not even reached that node. So, therefore, this node it does not even know the existence of a transaction. This node can also decide that I have this much space, so many kilobytes in a block, I have too many transactions. So, I will randomly select some of them, and this guy also has the same issue, right. So, he might have heard of the transactions or gotten a copy of the transaction that this guy did not get, but at least he got that. So, he puts that in, but on the other hand for the other transactions he has randomly chosen from the outstanding transactions that will fit into his block. There may be other reasons, we will talk about that. There may be an incentive reason why they choose certain transactions, it may not be fully random, but in any case all these blocks will look different, maybe not, maybe some of them will be exactly the same by virtue of probability, but there is no, they are not talking to each other deciding which transactions go to the next block. So, everybody will propose a block which may be slightly different. Now, when you propose a block, and if you broadcast that this is my next proposed block, this block should be part of the blockchain. If everybody does that, there will be a huge amount of data going in, and then every node that is keeping a copy of the blockchain will be confused, because you will get thousands of different block proposals and he would not know which one to take, right. So, there has to be some kind of a consensus mechanism through which the next block has to be chosen. So, let us see what happens. Now, as I said before that there may be a crash fault in some nodes while they are participating in the consensus process, or some nodes may behave maliciously. On top of that, the network has imperfection, right. So, not all pairs of nodes are directly connected, of course, right. So, there are long paths between them, or sometimes there is a segmentation in the network because of various reasons. So, not all transactions are reaching, or all block broadcasts are reaching all nodes very instantaneously, they might take time. So, there is latency, and then the network may have faults, because of that maybe rerouting is taking place and so on. On top of that, one could say that, well, if everybody broadcast a block, I will look at the timestamp on them, and then I will decide which one has the lowest timestamp and I will take it. But that is also problematic, because the notion of time at the various nodes which are geographically distributed is not unique, right. So, and then the clocks are not synchronized, there is no global clock maintained to do this. If there was a global clock, that is every computer has the same clock, then they could have actually done it much more easily by saying that the lowest timestamp one will be taken. But now the timestamps will be not trustworthy, because the nodes are at different time zones first of all, but even if you adjust for the time zone, everybody is, let us say expresses their time as GMT or Unix time, Even then there is a problem, because some clocks are slower because of various drifts and skews, and other clocks may be faster. So, unless you maintain a global time using GPS clock or some other protocol for time synchronization, this will not work. So, time stamp is not a solution to this problem. But while we go and look at the literature on consensus, we found that this problem of consensus is also called the Byzantine generals problem, and later in the course we will actually discuss this in much more detail. But the idea here is that if you have target enemy site and there are two garrisons which are disconnected from each other, except they can send messenger to each other, and they know that they cannot win this, attacking this and win this unless both of them attack simultaneously from these two sides. If one of them attacks and then the other does not, then whoever attacks will be killed completely. So, right. So, then we have a consensus problem, that we have two garrisons with two generals, and they have to decide whether they are going to attack or whether they are not going to attack, and either both of them have to not attack or retreat, or both of them has to decide to attack. So, this is the what is called the Byzantine generals problem. Now, the problem here is that if all the generals are honest and the messengers who are sent and back and forth are honest, then this problem is not a big deal, right. So, one general decides and then sends to this guy acknowledges, and then both are going to attack or both are going to retreat. The problem is that if you assume that one of the general could be malicious, or the messengers could be actually changing the messages, then this may actually fail. So, in that case they might this guy might think that the consensus is to attack, and this guy is actually think that consensus is to do retreat, and therefore, attack alone and then get decimated, right. So, therefore, you have to have a consensus that such that the honest general's opinion should eventually prevail when the entire thing settles. So, therefore, this problem has been a model for this consensus problem as Byzantine fault tolerance problem, so or called BFT. So, we will see a lot of this discussion on BFT later. So, but early result from 1979 I believe, by this is also called FLP result. The FLP basically says that if all nodes run a deterministic algorithm, then consensus is impossible even when a single node can crash, right. So, this is a very bad news, right. So, what we are saying is that solving Byzantine generals setting consensus problem or BFT, Byzantine fault tolerant consensus, is impossible even when a single node can be faulty, right. So, that is and in our case we cannot even guarantee a single node, it could be many nodes that are going to be malicious or faulty. So, then what do we do? But there are practical algorithms such as Paxos. So, we will also later talk about this, but Paxos is a Byzantine fault tolerant consensus protocol, and the way Paxos works is that, well, it never produces an inconsistent result, that is the some nodes are saying yes and some nodes are saying no, but sometimes it can get stuck and never terminate. So, remember we said that a consensus problem protocol should always terminate and they should always give a result, and all the good nodes or non-malicious nodes should arrive at the same result, and that result should be proposed by one of the good nodes, right. So, that was the requirement of a consensus protocol. Now, a Paxos does everything else except that it may not terminate sometimes. So, you may get stuck, but there are other ways to solve this problem. So, one thing that is interesting about impossibility results or NP hardness results or any kind of complexity lower bound result is that it is always the worst case scenario. For example, those of you know NP hardness. So, satisfiability SAT is CNF SAT is known as NP hard, right, NP complete problem. And it turns out many SAT instances are not difficult to solve, but there are very specific types of SAT problems which require exponential time. So, therefore, what we can actually say is that impossibility result depends on the very corner case or worst case. Also, the result of impossibility here in case of this FLP result is more about your assumptions, how the model is supposed to work and what their behavior is. For example, they assume that the model requires that every node does a deterministic activity. So, there has been Byzantine fault tolerant algorithms which work with almost probability 1, which are probabilistic or randomized algorithms. These models were developed to study systems like distributed databases, and right now what we will see as we come back is that this FLP result does not stop us from actually getting consensus probabilistically in blockchain. So, we will see that the probabilistically the consensus works in blockchain.